going?
Break.
Good. How about you?
It was good. Are these for us to grab? Or
yeah, so you can
cool.
look at them, use them as inspiration for your research paper.
Yeah, I saw there was a check-in assignment that was due on the platform, but it's like.
Oh, yeah, I haven't fixed that date.
Oh,
That's the one date
okay.
I haven't fixed.
Okay. So do you normally get these like every month, or these are just like the old collection?
Yeah, those are new ones that I get.
Fun.
I think the latest one is the red one, year in review or something. Yeah, our class shrunk, so.
Yeah.
All right. I'll let people finish kind of squeezing on in here. And if you're online, if you wouldn't mind just letting me know if you're here. If you don't feel comfortable doing that on YouTube, send me an email, just because I have to do attendance the first week. I don't normally track, right, online attendance. Y'all know that about me. And then, so as we kind of warm up, we'll do quick reminders, overviews. So if you've had me before, you know that I also stream these lectures, and so the link is here on Blackboard like usual. And we already have some of our cohorts out sick. I know, flu and norovirus and everything is apparently going around, so that is there. Or if you just want to rewatch them, many people like that. And then I tried really, really hard to get your calendar set up. So I think it mainly should match the syllabus. So you can actually kind of maybe use the Blackboard calendar. But the most accurate one is, of course, this concourse link. Hopefully that works for everybody. And then this thing loads, blah, blah, blah. Pretty similar like last quarter. And then as you probably know from your grades, again, it's all about the curve, right? So the exams are pretty brutal, but the curve, I think, worked out, and we're here. And so some just kind of things to think about before we dive into lecture and everything, reflections. And so hopefully people like the SOU trip. It was a little bit more of a sales pitch than maybe I thought they would do. But kind of the point was, right, they were trying to sell you on the small environment. And so kind of hearing feedback from like my former students, some of them are kind of struggling at the bigger Oregon State universities just because you become just a face. Your professor doesn't really care about you as much. There's no incentive, right? They have 300 other students. But that being said, right, don't get discouraged, right? I'm not trying to say, oh, go to SOU, go to a small school. It just means that you have to kind of fight more, right, for your spot. So that's what I'm saying. Hopefully you guys looked at NSF applications. Uh-oh. Hang on. National Science Foundation. Sorry, let me switch a cable real quick. Technical difficulties. Oh, this is weird. But I had posted it last quarter. I might have to repost the link. I haven't done that yet. But you should look at the NSF applications, right? Try to get to a research lab, because that's what's going to help you. So even if you go to a big, university, there we go. Sorry, let me map it. it's all about, building those connections, getting research opportunities. And so hearing from my former students, that's kind of the part that they're struggling with, right, at these big universities, is that you kind of have to fight for a research position. But that's why I'm saying, apply to other stuff, apply to internships, keep your options open. And I'll probably, like I said, I'll post some new stuff because I was also looking around during the break at other like scholarships, because you should check out. So I mentioned, NSF. And like I said, I'll post the link again. So National Science Foundation. And it's called the REU program if you want to Google it. But then if you don't want to look at that, there's also what's called the National Labs. I don't know if y'all, are y'all familiar with the National Labs? Vaguely? Yeah, so Lawrence Livermore is one of them. And so let's see, National Labs. I want to say probably Lawrence Berkeley is the closest. So here's a map, and again, I can post it. So unfortunately, with the national labs, you usually have to search each one individually, so it's kind of a pain. But there are sites in, so there's Pacific Northwest National Laboratory, and then Portland has, I'm not too familiar with this one, National Energy Technology, that's a smaller one. Lawrence Livermore, right down in Berkeley, is going to be your best bet. Accelerator Lab. But basically, right, I'm trying to tell you there's lots of opportunities, especially if you hunt around, so then you can start hunting, where you might want to travel. Sandia National Laboratories, right, pretty famous. Nashville Oak Ridge, that's another famous one. So just make sure, right, you're searching for opportunities, because now is the season for summer internships. So you want to make sure that you have a plan for summer. And so then just the other thing that I wanted to at least kind of touch on, especially as we go through this quarter. So this quarter is pretty math heavy. So our first chapters won't be math heavy, but after that it's just like equilibrium, algebra, a million equilibrium expressions. And so I know my exams, are difficult. Sometimes they're very math heavy, but I do that on purpose. And so again, it's feedback that I hear from my students. And so then they start telling me that they go to these big universities and people there can't do basic algebra, and they're doing well in all their classes because they can do the math essentially, right? So that's why we're going to keep doing a lot of math in here. So, just expect that it's going to be math heavy, just, that's how it is. Good practice for you though, so you stay ahead of the curve. And then when you continue on in your higher level classes, right, hopefully you won't have issues because you're going to have seen a lot of this math, right? And you're not going to be intimidated by an orgo test that's all blank, right, because you've seen blank exams before. That's what we're trying to prepare you for, because, that's what your orgo exam is going to look like. It's going to be blank, right? You got to fill it all in. And again, my students always tell me, like, hey, I'm doing great in my classes now. I understood, a lot of things, because we, built upon all these fundamentals. So we're going to be, of course, continuing to do that. And we'll start to lay down some of those orbital fundamentals today, too, which will be really good for OChem later. All right, I think I'm done yakking. Oh, yeah.
Can we use you as a letter of recommendation?
Yes, absolutely. So that's why I was saying I was a little worried because I didn't get a bunch of emails asking for letters of recommendation. So definitely ask me for letters. So yeah, we can. It's really good. All right, I think we're ready to dive into our chapter. So now we're going back to chapter 8. And so now chapter 8 is predicting right, geometries. And we kind of did a little bit of this last quarter. I can't resist of drawing structures and then drawing them geometrically correct. And so you want to pick up this sheet if you don't still have it somewhere handy. And so this is just kind of our VSEPR theory. And so what this is getting at is kind of how the orbitals are going to come together and hybridize, and then what that kind of means for the overall shape. And what's really nice, though, is this is a guide, so it's going to give us all the answers that we need, and then that'll really help us, again, build our fundamental understanding. So before we kind of dive into all these examples, let's first just remind ourselves. So what orbitals do we have? So let's just start off most basic. What do we remember? What's our lowest energy orbital? Yeah, S. And then what did the S orbital look like? So spherical, okay, nice big sphere, good. Clear those cobwebs out. And then what other orbitals did we have? So P, and we'll hold our thought there for now, because I know there's more. But we have our P orbitals, and then, so how many were there? Well, they could hold 6 electrons. Yeah, 3 orbitals. And then remember, they went in different orientations. And I'll call this Px. And it goes in kind of the plane of the board across. Py, I'm calling formally in and out of the plane of the board. And then I'll call this Pz here, so going up and down. And then, so this is useful information kind of going forward as we sort of talk about symmetry. But basically, Pz is usually assigned as what's called the principal rotation axis. Oh, I think I misspelled principal. Principal rotation axis. And so all that means is when we see high orders of symmetry, where we have like rotational symmetry, this is going to be considered Pz. All right, so we'll start with kind of these 4 basic orbitals. And again, our VSEPR theory is trying to tell us what orbitals come together and in what shape. And so let's just start kind of going through our classic examples. And so we have our key here. And so remember, this is just on the central atom. Or, whatever atom you're trying to determine the shape of, right? So if you're later on, when you move on to organic chemistry, if you're trying to look at the hybridization of a certain atom, right, you just look at that atom, and then you're just looking at that atom directly, treating it as essential. And then, so this is saying how many things are attached to it. And it could be, right, atoms or lone pairs with this electron pair big number group here. And so we'll look at a bunch of examples. And so let's just start with our 2 electron pair group. And look at some classic examples of this. And so the book gives this example, which I like using as well because, well, it's unusual. There are not too many examples of this. So we're looking at beryllium chloride. And then, of course, what you may note is kind of funny is that it's a covalent compound, right? We might expect it to be an ionic, formerly metal and a non-metal, but some of these species, they actually tend to be covalent in the gas phase, so that's what your book mentions, so you have to do kind of gas phase calculations to get this exactly. And so we know that, okay, it actually exists as this covalent compound, obviously also unusual since it is electron deficient, right? So it formally has 4 electrons on our central atom. And then, of course, right, chlorine has alone pairs. And so we don't care about chlorine and its lone pairs. All we're looking at is, okay, we have beryllium attached to 2 chlorines. So there's our 2 electron pair. And so, right, our kind of cheat sheet here is going to tell us the shape. And, of course, it's, right, giving both atoms plenty of space, so it's minimizing energy as well. But let's also think about, so what orbitals probably went into this? So let's kind of think about that. What orbitals are in line with each other to kind of bond? We can scroll back up. So what kind of looks like it sits in line? And we may have to change these labels based off of this principal rotation.
Hard to say, but because the charge is neutral in the center, when you send that charge, I would assume it's the central atom of the S orbit.
So S, so that's a good start, right? And so what you're trying to think of is like, how does it look like visually? So yes, right, your S orbital is sitting in phase, right? And then your chlorine is going to have, I'm just going to kind of simplify it here, since it's probably more of a p orbital bonding, but chlorine doesn't matter. So we have our S, but what else is kind of in line with this? And so again, I'm kind of thinking of rotation. And so not the same, obviously, so this is CO2, but I just want to show the shape and show right rotation. So where is it rotating around and what's also in line with that S orbital? Yeah, you said PX, but I'm going to just be picky and relabel it PZ because I want to call this the principal rotation axis, right? So its highest degree of symmetry is just infinite rotation around this axis, which again we're going to label as our Z axis. So that means formally we have our S orbital plus our PZ orbital coming together now. And then so we want to do this kind of shading here so the phases indicate things. And so you kind of want to, when they're the same shade, you can kind of enlarge it. So you kind of have this enlarged sp hybridized orbital. I drew that a little too exaggerated. So here's our sp hybridized. And so that's where, again, you can draw it more evenly. And so this is, right, our sp hybridized orbital. And so this is, again, right, on our beryllium. Let's go ahead and write our cheat sheet here. So we can add to our cheat sheet. I can scoot over. Where's my... Yeah.
If there's a bond between two atoms and one of them is a specific orbital, they're two separate orbitals. The bond between them always going to be a hybridized version.
So in this case, so yes, for all these, right, we're talking about the central atom, and then when it mixes to make these different shapes, these are all, yeah, hybridized atoms. But then we'll talk about, so, you know, we'll have to kind of examine each bond individually, so we'll get there. And basically, well, let's do that now. So we'll answer your question, or part of it. All right, so we're talking about sp hybridized. Let's redraw this beryllium to kind of better show what's happening. So now we're saying we have this sp hybridized orbital on beryllium. And then it's directly in line here with our chlorine. So I'm just going to simplify chlorine again as a kind of dot here. And then they're in line, so they're directly in line, head to head, facing one another. So this is a sigma bond here. So just a normal bond, right? So now we're just kind of breaking down what this is, right? So we're saying, okay, we have a single bond, and that's caused by this sigma bond that is formed from this sp hybridized orbital with our chlorine. Does that make sense so far? We're kind of like visually thinking about this. And so the other thing to keep in mind, and maybe this is where your question was going to, is, right, we still have our other px and py, right, that are hanging out on beryllium. So they would be, now we have to reorient ourselves, so I'll call this px probably in this direction. And then right in and out, we have py. I apologize, I'm not the best artist there. So right, so py. And so all we're saying is, right, they're existing, they're still there, and so perhaps they're available for bonding. And so let's take that the next step further, and let's compare it then to CO2. So just kind of think for a second, what's kind of the difference, right, between our beryllium chloride and CO2? So double bonds. And so let's start with that, right? So it still falls under our 2 electron pair group, right? So it doesn't matter the number of bonds. That hasn't changed. And I should put in my lone pairs just for completion's sake here. And so let's start analyzing this. So we have our carbon, right? We said that our carbon, well, it's going to be sp hybridized. We could even, let's go ahead, we'll take it really a next step further now. Let's start to analyze things. Let's go ahead and look at our oxygen so we can more accurately tell what it's bonding with. So kind of looking at it, examining the oxygen, how many groups are on there? Yeah, so going back right to kind of this chart, we're asking how many atoms or how many lone pairs are on that oxygen. So 1, 2, but then don't forget the carbon, right? So 3. So oxygen has 3 pairs to it, and so now we can use our cheat sheet to help us. Okay, this is starting to lay things out. So we have this trigonal planar geometry. Hybridization, we'll get into where it came from. So it's sp2 now. So let's take a second. So we'll go down. Let's look at sp2 hybridization for a second, what's happening. And so now we can kind of understand what this is trying to tell us, but then I'll mention where it breaks down. And so, yes, now we have an s orbital plus 2 p's, so I'll just formally call them pz and py. And so so of course pz, py, I might be changing my orientation. And so then that gives us our sp2 hybridized. So you have 1, 2, 3 orbitals, right? 1s, 2p, giving us 3 lobes. So there's our orbital.
Is that because there are 2 p orbitals and 1 s orbital?
Yeah. And so that's what went into mix. And like I said, this only holds true for these lower ones we'll talk about.
Does that sp2 orbital only apply to the central atom, or is it both?
So yeah, it applies to both oxygens, right? So now we notice, yes, both oxygens have the same hybridization. They have 1, 2, 3 things on them.
Why is that the case for that, but not for beryllium chloride?
For beryllium chloride, the chlorines, I just kind of simplified it as a dot, but it's just going to be more of one of the p orbitals bonding. I just decided to get into this one a little bit deeper. All right, so now let's start kind of rewriting this. And we'll keep track of what's going on. So we're saying we have our central carbon here. That's sp hybridized, 2 things on it. So there's our sp orbital on our carbon. Then our oxygens, right, we said they were sp3. So now I'm going to try to draw them, trying to show that there's an oxygen in the middle of this sp3 here. So notice, again, the orientation. So one of these sp2 hybridized orbitals is involved in bonding. The other sp2 have the lone pairs. So the lone pairs are in that geometry, right? So that's helpful for later. And so, okay, we have this direct, again, head-to-head interaction between our sp and sp2 hybridized. So there's our direct sigma bond. Sorry, sp2. I think I misspoke. So yeah, sp2. But now let's think about, so, oh, sorry. So yeah, I think you're jumping the gun for a second, because I was about to ask, right? So we have 2 bonds. We accounted for one of them, right, as a sigma. But then I think you were asking, well, where's the other orbitals? So let's answer that question. So we still have 1 remaining, right, on our oxygen. So only 2 went in. And so let's call it, I guess we'll call it px for good measure at this rate. So we still have, right, our px here. Is that what you were wondering about? Well, yeah, so then there's a px on each oxygen. And then you're right, so we still have also a px available on our carbon. And yes, right, carbon also would have a py, right? But now we're answering the question why it can't make a triple bond, because there's no py in phase, right? So now let's kind of think about that. And you really have to, think visually here. And honestly, like, that's the hardest part of orbitals, is like trying to freaking imagine all this in space. So like, if you're lost and confused, like, it's okay. Like, look at a lot of pictures. There'll be a lot of staring at pictures and things to come. So yeah, so right, just imagine, so okay, because we had 2 orbitals go into carbon. So yes, we have 2 left over. So py is just hanging out, in and out. But right, the py on oxygen is gone to hybridization, so it's not available. So it has nothing to bond with on this py. But maybe you were noticing that, well, it does have this px along with, right, our oxygen here. So now we're saying, okay, we can have this through space interaction where they're all in phase. So notice I put it where the dark shading is on the bottom and the unshaded is on top. And colors don't matter, right, as long as the colors match. And so notice, right, we have, again, this through space pi interaction. And so when it's through space, it is called a pi bond. And so now we can go back to our CO2 molecule, and we can write out that we have 2 sigma bonds, right? So 1, again, sigma just meaning your orbitals are head-to-head facing one another. And so we have our sigma bonds. Maybe you even want to label to remind yourself, okay, yeah, the first bond is always your sigma bond. And then if you have a second or a triple, right, that's going to have to be a pi bond. Sorry, second or third. So that means we have 2 pi bonds as well.
Can you say that last part again?
So if you have a triple bond, then that means that you have another pi bond, right? So that would have meant that you have py available, and then there would have been a triple bond.
So, my understanding, the sigma bond, whenever the bonds are 30 degrees against each other.
Yeah.
Is a pi bond anything at any other angle?
It's always a through space.
So like 90 degrees?
Yeah, kind of through space, but we'll see like other d orbitals where you can kind of have like.
Does it have to have that strict angle? Or
Well, it's usually going to be across like this.
across any space?
Yeah. Yeah, that's always a formality. Like, so if you go on to like, especially inorganic chemistry, it's always Z. But. Well, it depends how you like label them, right? But if we're calling the principal rotation Z here, then that's going to contain, right, your sigma bonds mainly, because that's from your hybridized head-to-head along that. Yeah, because remember, PZ is running this way along that principal rotation.
You mentioned that oxygen has sp2 bonds, and carbon has an sp hybridized bond. Is that an sp1 bond?
Sorry, repeat what you said. So you said oxygen had sp2.
Yes, and then carbon has an sp hybridized bond.
Yeah.
sp1.
Yeah, you just don't say sp1, you just say sp. All right, so let's continue with our 3 electron pairs. I'll make a new page. So 3 electron pairs, which we did look at, right, with oxygen. So we have AX3 is kind of the abbreviation. So we'll start with AX3. So we're looking at our 3 electron pairs. And so AX3 is going to be, right, trigonal planar with the X meaning that they're all atom substituents. And you may remember some of these, right? Aluminum trichloride, gallium trichloride, boron, all the boron compounds, boranes. So those have nice symmetry. And so like we were looking at before, so I'll just simplify. Again, just think of chlorine as a point here. So of course, right, geometry is trigonal planar. And we said this is sp2 hybridized from, again, I'll just rewrite it, our 1s and 2 p orbitals going in, giving us our 3 lobes. And so again, right, we have our single bonds, just kind of simplifying chlorine as our point, right? We can see we have our head-to-head, again, interaction. We can kind of rewrite our aluminum. And then, again, I'm just going to put chlorines as a point. And so let's look at SO. So write the structure for SO3 for me, so do a little warm-up. You tell me. No, see what you get. Let's see, Caleb's here. I feel like we're missing a few of your classmates. Do we get a structure for SO3? How many bonds did we get on all those oxygens? So did you have all single bonds or? Yeah, I got double bonds. And it's kind of the preferred structure, so that gives sulfur, right, a 0 formal charge, so that's kind of nice. Even though it does have a lot of electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it is hypervalent, but that's okay for sulfur. So 12 valence electrons on sulfur. And then we just wanted to look at this structure to again kind of show that, okay, even though it has all these double bonds, still just 3 things attached to it. So still trigonal planar. The only thing that's different, and we can analyze this, is, right, there's obviously some pi bonds, so let's look at that. And so we can draw it out. So again, our sulfur is sp2 hybridized along with all our oxygens. So I'll put sulfur in the middle here, sp2 hybridized. Then let's see it, how it's going to make a bond with our oxygen. And then again, right, it has those lone pairs occupying the other orbitals. Oxygen. So right, again, we can see, okay, we have our head-to-head interaction from our sigma bond. So all sp2. And then, of course, right, we want to answer the question, well, how do we make our double bond? And so what orbital do we have available?
There's oxygen orbitals. There are 3.
So which one? Well, remember, 2 went into bonding, though, right? So that's what we're saying. So from what we had said, if we want to call them PZ, PY, right, let's just say PZ and PY went into bonding, but then that leaves for all of them this up-down orbital, right, that's not involved in hybridization, which we can call PX. Again, right, your axes can change. So it's up, down, right? So we have these available p orbitals. And so, okay, that's how we made our double bond then, from our through space interactions to give us that pi bond.
Can you label the p orbitals on the sulfur, like the PZ and the P1 too?
So the sulfur, remember, they're sp2 hybridized, so it's just these three things now went into making that. So right, kind of remind yourself it was the S plus the two P's that gave you that flat lobe-looking structure that's ready to bond. Does that make sense?
How is the s orbital involved in the bonding?
So the S just gets absorbed into this sp2. So it's like the mathematical combination. Just adding them gives you the three even lobes. So yeah, that's where your S went to kind of mixing right in the middle there, because it's, again, pretty much head-to-head direct.
Is the letter that you choose for the orientation arbitrary? That very well be px plus py, and then you have pz comes?
Yeah. So it probably should have been PZ given the principal rotation, but I didn't want to go ahead and like recorrect and confuse everybody. Yeah, because it doesn't matter too much, these labeling. We just want to know that there are three of them and then kind of keep track. Okay, well, if two are in the hybridized, that means that there's still one hanging out to either hold a lone pair or be involved in bonding or do something.
And whenever you have a double bond, is that always with a sigma bond and a pi bond?
Yeah, so that's what we're catching, right? So then, and then like we'd said with the triple bond, then we have to have a sigma and two pi bonds. And so let's look at, just for completion's sake, we'll look at an example. So then we have this special vent case, which is sometimes called V-shaped vent if you look at certain textbooks. Otherwise, they don't make a distinction and they just say vent. And then you have to go by the degrees here. So that would be this angle. So this should be about 120, which you expect, right? So obviously you divide a circle by 3, so that gives you 120 per angle. But then your lone pair forces it down just a little bit more. So that's why it's a little less than 120 at 119. And so see if you can draw out the structure for SO2.
I have one more question.
Oh, yeah.
On this structure with all the orbitals, we have pi bonds, and they're connected to the px bonds. And there's three of them connected to each double bond to the oxygen and the sulfur. But there's only two orbitals, px and the sulfur. So how does it create three?
It's just a through space interaction still, because it's just about like that they're in phase, and then that means that you can have, right, electron interaction there in, because it's just occupying, because right, it's now we're saying, well, where are the electrons, right? And so we are asking, okay, we're piecing together like what orbitals are making the bonds, right? So now we're saying,
It's not one orbital, it would be multiple orbitals.
yeah, because it's, so right, even though we have just one px, it's still all in symmetry with them, so they're still all in phase. And then, right, this is, we're going to see where it can lead to like resonance, so yeah, just kind of hang with it here. And so notice, right, what we're trying to show is there's through space interactions too, on top and on bottom, just to be clear, right, because it's all through space, right, they're all in phase, and so it creates, right, all this basically. Now we're saying this is where the electron density is, so we have these clouds, right, in these p orbitals where our electron can be occupied.
Do the sigma bonds count as through space interaction as well?
No, so the sigma are always head-to-head, right? So remember, those are going to be more direct interactions. Well, it's probably more of like density of the like probability density. So if you have a sigma interaction, right, that has a much denser probability of finding the electron, and then the pi is just tends to be more diffuse, but they're still going to be moving all throughout that pi system. So it's also answering, right, like what system it's in, because either the electron's trapped in the sigma system or it's like running around in a pi system. And again, we'll get to delocalized pi systems and what that means. All right. Oh, yeah.
For those, it's an sp orbital and then another p orbital.
Yeah, so these are all SPs,
So for
or SP2s, right?
S2 and p.
Oh, sorry, I didn't hear what you said.
For like counting the electrons, is that what dictates how many orbitals I have? So when they're filling.
No, because now the shape, right, dictates, because it's both things. So, right, we do our Lewis dot structure with the electrons, right? But then the orbital diagrams takes it a step further, right? Because now we're saying, well, where are these electrons kind of located?
Yeah, that's determined by the s and a p and another p. Is an s and two p's to create the sp orbital?
Yeah, so S and 1p to create the sp orbital. So maybe we'll do a cheat sheet somewhere. So we'll start it over here to remind ourselves. So, right, recap, so SP, that's equal to an S plus 1p orbital. And I'm just going to say PZ, right? It doesn't matter the labeling. Could depend on the orientation. And then we said, okay, SP2 was now 1s plus 2 p's. And again, I'll label them, but obviously the label is arbitrary.
The nomenclature of those, like, of you labeling, is it typical to start with the PZ and then kind of work down to the X, or as long as you stay consistent?
So it goes back to the PZ should be the principal rotation, and so that's kind of why I picked it, because we saw some cases where yes, PZ was right along that principal rotation and the sigma, but yeah, it changes from situation, or you could just call anything however you feel like, really. All right, that's probably a good spot for a little break. So let's take a break. Oh yeah, what I wanted to say is I dragged all these chemical magazines here as inspiration for your paper. I forgot to talk about your paper. So I need to fix the assignment dates in Blackboard, but basically probably at the end of next week we'll do like a topic check-in. So I want to know like what your topic is, and then kind of like now your final papers. But that being said, because I don't know who is in the class and staying, and now we have new people. So if you need papers, just resend them to me, right? If you need access to papers, so I can get them for you so you can read. Or again, right, if you want to change your topic, feel free to look through, kind of get new inspiration. Feel free to borrow these, take these home. They mainly just sit in my office, but I want you guys to at least enjoy them. So yeah, feel free to look at those. And then, yeah, take our 10-minute break so we can be back around noon.
So just say so. I understand. It's like that. How are they directly? Sure, they feel like that. I get that they have the energy from the empty space to fill that, create that bond, but how and why?
Yeah, so those
The series
also
thing.
would be, right, yeah, well, so that's what gets funny. So now the principal rotation on these is group here, so you can rotate kind of threefold, but yeah, that's where the orientation is always changing. Yeah, yeah, so it's kind of 3 orbitals make 3 loads.
Yeah, I feel like I'm being hard.
Oh, so then those make just like the next way. Yeah.
I know. These people like study
Oh, I
those
so
stuff and then.
Oh, it's the one that makes square 1, 2, 3 costs.
Okay, I
Just trigger it.
just, okay.
Or it hasn't yet. Yeah. I know.
Yeah. I mean, we'll go over it as a class, so we don't like talk over it. Because the information, maybe there.
You should what, 4, 2?
We do 2.
No, she's a 4, 2. Is she a 4, 6?
Sure? Yep, I looked up. You can't like the secretary knows.
I mean, lectures are usually.
Oh, yeah, she's a
Yeah. So she's in with us.
Like, obviously.
super premium now.
Yeah.
Yeah. Yeah.
Do you know what topics will be?
Yeah.
I have.
Normally they're under, they're like in the blackboard.
Modular
Section, I think
English on it, and I
they're like under each week, there'll be a section with the notes,
save it up a bit. That's add like
module that's in there.
Oh,
You know what, yeah, I think she uploads it.
Really?
Turned out that I like that there were all these chemicals that were being put into like what people use.
Really?
And so they wrote this article. Started getting really weird calls.
Uh-huh.
It's like crazy phone calls from like unknown numbers. So like stop the article.
Yeah, man, you know, I'm joking. Really?
No, it was like, and all these people are like,
I'm not aware of this time of
symptoms
day.
of poisoning essentially.
Yeah. That's crazy.
Yeah.
That's insane. Where'd you hear it? That's insane.
I read it on the LA Times. Yeah, no, it was.
Oh, yeah.
I bet it was. How much of the community?
sync up with my last
Oh,
chapter in
yeah.
and like it won't open. So
Oh, dude, from the scary
Yeah, I
phone
have
calls.
it.
Oh, shit. Don't check him out.
No, I don't. We haven't started on this. Man.
Theoretically, they have been writing about it.
I mean,
oh, you
Yeah.
stupid
sax.
English Shepherd? Okay, so for my topic, I'm thinking I want to do something like with chemistry and environmental science.
No, like.
Do you have any suggestions? Because like I was looking, I was like maybe something with like pollution, like figuring out how you can use. Okay.
Yeah, I mean, there's
I was
lots.
looking at spectroscopy.
I mean, you could even start with just like the legacies of like water crisis, something like that.
scientists that found this really rare species of beetle. It only lives in this very, really, really hot air climates. And so it evolved
It's
basically
Tuesday.
on its own.
Remind me what you, oh, environmental. The other thing that I was thinking is somebody was interested in like environmental law last year, so I don't know if like that'd be something you'd be interested in too. But you could at least look at like different, I think there are case studies, I might pull them up, but there's like, you know, different, what happens, I think methyl bromide is one of them.
The opposite of
Wow.
Yeah, but there's like some contaminants and then, you know, the lawyers get involved and clean up and all that. So you could kind of take it that way too, though, is what I'm saying, is like you could kind of look at like the law side, the policy side, or yeah, you could just get into the chemistry side, what does it take
Oh, you're
to
trying to remember
physically
his name.
clean it up? Yeah, so there's lots of different ways. So you could run with it.
Physics.
Yeah.
Thank you.
I'm doing.
Yeah, I would, is this like paper like more just like a research kind of report paper?
Yeah, yeah. And it's also that fun. Microplastics is also
Oh,
always
oh,
good.
that sounds like a good one.
Yeah.
That sounds like a pretty good one.
I have a question. So I'm reading this article, paper on which is the idea that it was proposed by this physicist, it's a physics paper.
Yeah,
not a
no,
chemistry
but
paper.
I'm super excited. But
But it's a principle that, and the common model is, I think it's called an Atlas machine. It's got two weights on it.
finally.
So if one weight is twice the weight of the other one, you get the maximum amount of power out of that. So that has been applied to things like
There you go, you learned
circuits
it.
and circuitry and things like that. But I wanted to look into chemistry and try to apply to that.
Yeah, I mean, it applies to photosynthesis, and that might be
Oh,
kind of a good
What's
segue,
climate
yeah,
change?
because I don't know if that ties into
I'm already having to write a
like any
10-page
sort of
like 10-page essay on climate change. I
solar
don't really
panels
learn
and
more
like
about
the
climate
silicon.
change.
Yeah,
hit my
or just
limit.
like, tuning like the sensitivity.
I'll get there when I
of
actually
that.
get into
The
environmental
application of
science.
photosynthesis was studied in Puerto Rico, and it was done on this really tall mountain. They were trying to find what's the optimal level at which maximum amount of sunlight can
Here, I
produce
believe, it's
the
a
right
satellite
amount of
that's
moisture.
It's just
And
a
those things sort of bottoms out. So
Not
it's a certain elevation, basically the average plant cover.
Really?
Rather often point.
Yeah, that's like.
Okay, then.
I'm going through the article,
That might be what
and
this
it's
is
got all these like different calculations.
part of the like thing about water on
I think so, I don't know if you're the one to talk to.
I mean,
water at one point.
it's also like, you don't necessarily have to get deep into the weeds, because you just want to like more present the results.
So I'm just interpreting.
Yeah, for the most part, just kind of interpreting. Like, you can put several papers together too, just like, here's what's kind of going on in the field, like, so that's where you have the freedom to take it. Look at, a few applications of this, and whether there are, or,
Not like nuclear.
That sounds really
Yeah, it's a lot of like a lot of places.
yeah, I mean, that's,
I'm thinking a lot about there's a specific theory of 2.5 that in order to actually rate neutral reaction is dangerous for explosive. And I want to sort of find like the level of density which that could happen.
That sounds pretty cool. I like that.
yeah.
It takes a while because everything is required.
Yeah, I mean, I would just try to focus on maybe like
I have to
one.
find the papers first.
Yeah, and so just email me if you need help.
Thank you.
What I'm doing. Do we read an article and we just do a report on it?
Right now I think we're just gathering like research material and looking for a thing that we want to write a paper about.
How she meet that?
Yeah.
Last
Interesting.
Yeah.
I learned something on environment.
She mentioned the same on last semester. Great.
Oh, so land, water,
Yeah, like just having like white story. I didn't either.
Hydrogen electrolytes.
But then she's no
What's it called? Electrolyzers.
Oh, yeah, that would be a good topic.
I know that I did that last time. I wasn't able to go again.
You need some agriculture.
Yeah. Yeah, and you can always, refresh it, write it new, get new sources. So if that's a topic that you're, really passionate about.
There's also first term.
I mean, and then I'm like,
Yeah, I mean, it was the same ones we did, like when I haven't changed anything.
Right, I just need to remember what chapter it was.
I would have to send you the syllabus.
I just wanted to like review it has been.
Oh, yeah, I can email that to you.
Yeah, I just want to get like a quick review.
Oh, yeah. Sounds good.
That's like the whole point of the line too. It's like Hello. So I'm technically not registered for the class yet, and I was told to come talk to you about that because I got a D in my math class last term, which that like acts as my prereq requirement. So I was told to come ask for basically like an override key.
Oh, okay.
Like I would have passed my math class if I had done the online homework, but I kept forgetting about my own math thing.
Yeah, I will do that, like, as soon as we get done with lecture, basically.
Yeah, no, like no, I just wanted to let you know.
No, we gotta do that fast,
Yeah.
because isn't the deadline tomorrow?
I think it's Monday is the drop deadline.
Okay, I wasn't sure.
Yeah, you're good. So, wait until it's on Monday.
Well, maybe you could put like a positive spin, like how to.
All right, are we back from break? Oh, yeah, please, take them home. They, otherwise, like I said, they just sit in my office and collect dust. All right, so as we head back, did we get a chance to draw SO2 from last time? So what did our SO2 look like?
That would be like a CO2 structure, so like this little oxygen on the sides.
Well, count your electrons though. So how many electrons are in the system? 32. What about just valence electrons, right? So 18. So then kind of put them around. So if I do what you were saying, like CO2. Yeah, so it needs, so we have, where are we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we need 2 more. So 17, 18. And then for my sanity, I just want to redraw it, but that's just me. I can't look at that.
Does sulfur tend to form double bonds?
Yeah, so sulfur likes forming a lot of double bonds, as we're seeing. And again, a lot of that is from it being large enough to accommodate, which we'll get into.
Physical radius.
Exactly, physical radius. And so really the only difference that we want to take away is, of course, right, still sp2 hybridized, so all these are actually sp2. And except, right, one of these sp2 hybridized orbitals on our SO2 is just holding a lone pair, right? And so again, right, we're just kind of noting, okay, occupied by a lone pair, so it's in this geometry. And then we understand, again, where the V-shaped vent comes from. So V-shaped vent, or again, just vent perhaps, depending on your reference material. Oh, and then I do want to make a distinction now. So we can talk about electron geometry versus geometry. And so electron geometry just refers to the parent shape that it's in. So really referring to this sp2 shape. So what shape is that? Yeah, so it's just, right, our trigonal planar still. So again, we're just describing the orbitals with the electron geometry. And then when we ask for geometry, or sometimes molecular geometry more specifically. Now we're asking just for the atoms, and so we ignore, right, the lone pair and just say V-shaped. Yeah, question?
So when you have a bent molecule like this, or a critical bent molecule, do those sigma bonds and pi bonds fall in a specific place on the atom, or do they fall inside of the clip?
Yeah, so mainly, right, the s orbitals, again, since they're head-to-head, they're going to be more kind of in the middle, and then, yeah, your pi orbitals are going to be kind of on the outside, right?
On the outside.
Yeah, and you'll get a feel for that today. And maybe let's take a second to talk about our lab, actually. Since lots of people are ill, and then lots of you have questions about MOs, which is perfect. That's what it's for. And so I organize things differently for some reason. Anyways. So lab 1 is under here. So we have all the labs listed. And then I'll just look at the PDF for fun. And then decided to give y'all a break from doing the abstracts, right? We had a lot of practice last quarter. Now we kind of want to shift to researching, right? Getting ready for the paper. So I want our focus to be on the paper this quarter. So that's why I kind of threw out the abstracts since we had practice with that. And then this first lab uses WebMO. So this is all online. We'll go ahead and do it right in the computers in lab today. But if you're ill, you can do it at home. And so what we're going to do, and you can play with this too, is we go to webmo.net/demo. And this is their just open server. It's a powerful supercomputer that we can run calculations with. And so you can do this at home too, right, when you're bored. And so I'll try to run that while we work on some other stuff, and I'll kind of show you, yeah.
Is it possible you can tell us like one or two good examples of
I'll see what I can find. So I can dig up from the archives. All right, we'll keep marching on for now. I'll go back to WebMO, and again, we'll play with it in lab, so if you're hungry for more orbitals and pictures and what they look like, WebMO will be a good thing to play with. All right, so let's look at our 4-electron pair group now. So now we're moving on to sp3 hybridization. And so let's go to our cheat sheet and remind ourselves what's going on. And so now sp3, so as you can imagine, now we have one S and all 3 P's in there. X. Oops, I think I changed my axes every which way, and that's okay. So, right, 4 orbitals become then our traditional tetrahedral looking lobe thing. So 4 even lobes, again, in our tetrahedral. And so, of course, now let's talk about some of our classic examples. Yeah, Hunter?
any sort of polarity like
So right now we're not focusing on like polarity or anything, right? So that comes into play later once you start changing the substituents, right? So you just start with like a blank sp3 hybridized, right? And then any polarity, then you can start adjusting like your lobe size. Jonathan?
The PY orbital with the sp2, I noticed that like it was invisible.
I think I just wasn't like consistent with these. Yeah, and I'm not the greatest artists, unfortunately. So let's look at just the 4-electron pair group first. So what would be our classic examples of that? So not ammonia, but ammonia is the same electron geometry, which we'll get into, but not AX4 with 4 substituents. Yeah, methane. So that's the one I was looking for. So right, that's the classic example that we all remember and love, hopefully. And then we can think about all our other group 4 analogs. Silicon tetrachloride, one of my favorites. Germanium tetrabromide. Okay, I'll stop there before I get crazy. And so then we can draw our structure. So of course, methane, we remember what methane looks like. And then now we're really appreciating the 3D structure of this. Again, I'll just remind us that our fat wedge here is showing that it's coming out of the plane of the board. And then these dashes, right, are showing that it's going behind the plane of the board. And so like we were saying, so our electron geometry is, of course, tetrahedral. And then, in this case, right, fully symmetric, our molecular geometry is also tetrahedral. And then, right, not too exciting, I'll just kind of redraw it here. But, right, we can, again, just appreciate our sp3 lobes. Well, hydrogen just has an s orbital anyways, so we don't have to make much of an assumption there, treating it as a point. And then again, right, we're just appreciating all our sigma interactions, which, right, we expect since we just have a single bond. So yes, probably just sigma interactions there. Feel good about that one. And so now let's do our next example in that family. So going from tetrahedral, now we're removing, and I should have made my methane molecule a little faster here. All right, so we were at methane, and now I need another camera, so more camera work. And of course, right now we're just going to take off one of our groups there. So now what classic example is this one? We said it earlier. Oh, now's no, the other one you said. Ammonia. Now's ammonia's moment. So ammonia is our next classic example on this sp3. So again, just removing one of our substituents to give us our trigonopyramidal molecular geometry, still tetrahedral electron geometry, still sp3 hybridized. And so now let's draw out, so we'll call this AX3E. So we're just saying we replace one of our substituents with an electron pair. So I'll draw out our ammonia. And we can, of course, list other examples too, so PCl3 or phosphine. So we'll draw out, I'll go back to nitrogen. Nitrogen, of course, it's lone pair. And drawing out our hydrogens. So electron geometry, tetrahedral. and then molecular trigonal pyramidal. And then what's your question?
When you're drawing a tetrahedral molecule, do you always put the sort of the bond facing in, the bond facing out right next to each other?
Yeah, the stereochemistry, this thing, or?
Yeah.
Yeah, I mean, I like drawing it this way. I think there are kind of like other ways to technically draw tetrahedral structures, but I just draw it this way most of the time because that's like the clearest.
Do they have to be adjacent to each other?
Yeah, usually. I mean, you could like flip it, rotate it, but you still ultimately, right, have to make some sort of tetrahedral structure. Yeah, so you could put like, the wedge on this side, that's fine too.
That's an SP3.
Yeah, so nitrogen, right, so let's go through that again just for clarity. So still sp3, and we can, again, just appreciate where everything is at. So nitrogen in the center, let's draw out our sp3 orbitals. So now we're saying, okay, our lone pairs, right, are occupying one of those. And now we have our bonding. And then I'll put hydrogen as a point, since it is an S anyways. And so again, right, our 3 bonds, obviously head-to-head sigma interaction. And again, right, our lone pair occupying this position. And so this, we'll get a little more into it. But again, this is where identifying your hybridization is really important, because again, as you move on to OChem, you'll get into scenarios where you'll need to know whether this is hybridized or not and in which way, because that'll tell you, right, whether you can have a pi bond or not. And I'll point out these scenarios more specifically, but basically, right, this one, since again, it's sp3, everything is fully engaged, right? So this nitrogen, what I'm telling you is it cannot participate, right, in any pi bonding system here. Does that make sense? That's basically what I'm alluding to, but well, we'll do more examples, but like that little basic principle gets carried on in OChem like 1,000 times, and like honestly, I did not understand it like taking OChem. So I'm trying to teach you so you're not like me.
So if there aren't any pi bonds in the system, but are there any pi interactions?
Well, that's what I'm saying, right? Because we ran out of orbitals, right? We essentially ran out.
Oh, I see.
Yeah.
Hydrogen only has S bonds, or has only S orbitals.
Yeah, and then all our other P's, right, are already involved in hybridization.
So you can only have those the 3 orbitals?
Yeah, yeah. So that's what we're getting at, is we have no available p orbital, right, to do anything with. But like I said, we'll actually see this later. I'm just kind of alluding to why this is so important. All right, so let's keep going, and we'll keep the questions coming, because again, right, this is good. You're trying to visually see it in your mind because you want to see these molecules and their shapes, because that will carry you immensely through OChem. Like I was told, there's so much hybridization in like apparently the first quarter OChem at like OSU or something. So, nail this down now so you're breezing through OChem later. All right, so let's try the next one. So AX2, E2. Let's look at the picture. So right, this shape, bent. What would our classic example of this be?
I'll
Ready?
say CH2, but I mean,
Yeah, think more commonly. It's a common molecule.
Water.
Yeah, water. So water, classic example. All right, H2O. Oops. And so just writing, okay, we have our lone pairs. And so I'll take my molecule kit again, right? So obviously we're back to electron geometry. And so what's our electron geometry? What family did it come from? Yeah, or we could also ask, right, what hybridization? So, right, still sp3. All we did was, of course, replace two substituents with electron pairs now. And, right, you can, again, draw it every which way if you're an artist. And so then our molecular geometry is just bent here.
Is it implied that there's stereochemistry happening with the two pairs electron velocity?
Once you lose your two substituents, you lose your stereochemistry. Yeah. So we'll get into at least a little bit of stereochemistry, but basically we need 4 different things. So. Excellent. All right, let's get into what I call now kind of our funky ones, since we're not going to totally get into the orbitals, or at least maybe not at this second. All right, so now back to our Vesper chart. And so now we're going down, and so it's going to be sp3d formally. But now this is where the kind of naming thing that I'd been telling you breaks down. Because there's no d orbital in there really, so the sp3d now is just to refer to the shape. And so it's really just a mixture of s and p orbitals, and really p orbitals mixing to give you these shapes. But we're kind of not going to go into all the weeds because that kind of gets a little bit too detailed. But again, we want to appreciate the shape, so sp3d. And so what we're trying to say with this sp3d is if we follow the pattern before, so now we have 1, 2, 3, 4, 5 kind of orbitals-ish. Again, we won't get into it right now, but it gives us the shape of a 5-lobe, like so. And again, I kind of want you to see the p orbitals in there because, again, there are no d orbitals actually invoked. And if you want to have a discussion later after class about this, if you're really bothered, we can. But otherwise, we'll just accept this, right? So no d orbitals actually used. So it's a little bit, I'll admit, it's hard to see with this one, but I think once we look at the 6 electron pairs, it'll be a little bit easier to see how we can just invoke our p orbitals. But this one does involve a little bit of mixing here. And so again, we're just accepting the shape. So notice, right, we have our up-down shape, and then these are all kind of in the middle, right, kind of trigonal planar in the middle.
Is there any standard way to making sure that
So I could draw it, so let's go back to our new page. So maybe this will help you. So 5 electron pairs. And again, write sp3d, just referring to the shape at this point. And so looking at AX5, let's just start with PCl5, so classic example. Yeah. And you may remember this one right from last quarter. I think we might have drawn it out at least. And so I'm just drawing the chlorine. So right, obviously they're up, down in the principal rotation axis here. Chlorine's off to the side, just in the plane of the board still. And then, yeah, I'm going to go ahead and use this wedge to show, right, that chlorine's coming out now. And then our other chlorine is going behind the plane of the board. And so then can you guess what the geometry of this? Of course, electron and molecular are the same for this one. And you can look at your cheat sheet too. What's the geometry? Yeah, so trigonal bipyramidal, right? And so you can just kind of see that there's 2 pyramids. So one on top, and then invert it, right? One on bottom. So that's where you get the name. So trigonal bipyramidal, however you want to pronounce that. So that looks good. So now, take a second, see if you can practice. So think about what's happening. So now we're going to remove one of our substituents, replace it with our lone pair. And the classic example of that is SF4. So see if you can kind of draw out what that might look like. So how's our SF4 coming along? And so probably the easiest thing to do is kind of think about removing this chlorine. And then, I don't know why, I like kind of reorienting it. Well, I know why. It has to do with the name of the geometry. And then again, I'll try to draw the shape. So right, kind of showing the fluorine's kind of coming out. And then our other one's going back behind the sulfur. And so maybe this looks like a piece of playground equipment. So what's the molecular geometry? What does it look like? You can look at your cheat sheet too. Yeah, sawhorse or seesaw, and it depends on the reference, and I'll accept anything. So sawhorse, seesaw. I mean, I guess you could even call it teeter-totter geometry if you really wanted to, but something, right, to just kind of indicate that it looks like that. And then these lone pairs will probably be pushing down, just a little bit on those floorings. I won't have to see it.
So there's no term for the, you'll notice there's electron pairs that affect the geometry, and there's some at the ends of the atoms that don't. Is there like a term that differentiates the two?
Well, it's mainly because we're looking right at the central atom, because we could still examine the fluorine, right? And so what do you think its hybridization is?
The SP1,
Well, how many things is it attached to? Wait, count it again.
oh, SP3.
Yeah, SP3, right? So we just don't bother showing them, right? So you have 3 SP3 that have the lone pair, and then the other SP3 is involved in bonding. So yeah, it does have that tetrahedral shape still, but
That triggers any like thermal lock.
yeah. So either it's, well, yeah, so you have to examine it, but they're going to tend to be SP3, but then again, only one of those lobes is involved in bonding, so. And that's why I usually simplify them as a point anyways. All right, sorry. I was trying to show Gaussian, but I'm still working on it. All right, let's do another. Let's continue going down our geometry line here. And so again, right, these are all electron geometry of trigonal bipyramidals. So we did sawhorse. Now, I gave it away, but we'll do T-shaped. So let's practice some of those classic examples. And so a lot of these T-shaped ones are weird halogen compounds. So of course, these are AX3, E2 now. And so IF3 is always a fun one. One you also see is like II3, which can confuse people just because it's all iodines. But try to do it maybe IF3. So just kind of draw it out. What does it look like?
For that SF4, for the sulfur fluoride molecule, you wrote down the molecular geometry with the electron geometry, the trigonal pyramidal.
Yeah, exactly. I'll add that in. I wanted to just kind of show you what WebMO looks like and what kind of you'll be doing. I admittedly probably should have picked a simpler thing to show you. I just kind of got overexcited. And so what I mean by that is, so the thing that WebMO is going to do, and we'll talk about this in lab, but basically it's like trying to solve the Schrodinger, but with all these like simplifications that have been done and all these computational chemists have developed over time. But then literally, like, it spits out everything. So that's why I said I probably shouldn't have picked something so complicated, because now if I'm trying to show you the MOs, and this is what I mean, so we look at like this lowest one, right? So that's probably just our core S electrons, right? So like completely non-bonding. And it's going to show you every single one, right? So now it's showing you, oh, here's your core over there and like all this other stuff. And so let's try to skip over to where the action is. And so right now, this one, starting at this value, probably looks like our sigma bonds. And so also notice what it's going to do is right now it gives us, because what WebMO is doing is now it's giving us really the probability density map. So then we can see, okay, right here is our sigma bond in the probability density map. And then, so let me skip. And so, so then we were kind of talking about the pi system and how that works. So, again, we mentioned all those p orbitals being all in phase. And so then this is what it can kind of do, right? So now we have this delocalized pi system, and that's what's nice about this WebMO. It's like, oh, now we can kind of put the pictures together with kind of the theory that we're doing in class. And so now we're kind of saying, okay, yeah, now I see this delocalized kind of pi system. And then again, right, these are confusing. So it's hard to decipher exactly what it's showing us. Plus, it's going to start giving anti-bonding orbitals, which we haven't talked about. But again, you'll at least get to play with it. You'll get to play with the shapes that it gives you and kind of get at least a baby feel for computational chemistry. All right, so back to IF3 or any sort of these variations. And so if we're going for T-shaped, I like to go back to our parent electron geometry. So looking at this and then knocking off probably these two chlorines, right, to give maximum space and give our T. And so now I'll draw this. So and we can put right our lone pairs on the side over here. And fluorine, fluorine, fluorine there. So we have two lone pairs. And so what's our electron geometry again? So trigonal bipyramidal. And then what was our molecular geometry again? T-shaped. Excellent.
So the electrons do have stereochemical properties?
Well, I mean, they're like occupying space, right? But we don't really say that it's a stereochemistry, right? So you still want to use your Vesper to kind of show you where it's at, right? So it's...
How do you indicate that in a graph like this?
Well, this is kind of implied that way because you usually don't like draw stereochemistry on lone pairs. So you just kind of look at, notice that all these are flat. And that's where, again, right, the chart kind of helps us in case we don't draw everything perfectly or we don't quite interpret it right, we can go back and see. And they did show stereochemistry there, but honestly, like, that's usually not done, so. Let's see. I think we can think we can at least round out our linear. Let's see how far we get. So again, we're still in our 5-electron pair, so we're still with our trigonal bipyramidal electron geometry. And so now we want to look at AX2, E3, and so the classic compound for that is xenon difluoride. So go ahead and sketch that out. What would that look like? You can probably imply where the electrons are going to be located. And so drawing out your structures, probably put those fluorines on what I would call the axial or principal rotation axis position, right, up and down. And then that leaves our lone pairs all in the middle there. And again, right, you'll have to imagine them being planar in the middle, drawing that as best as we can. And so like we were saying, so we have our electron geometry, which was still in our trigonal bipyramidal family. And then our molecular geometry. So what's our molecular geometry? Linear. So don't let these confuse you either. So we can keep going for a second. Still 10 minutes, so let's see how far we get. So right, our last group, electron pair 6. And actually we can take a second with this one, because this one, like I said, it's a little bit easier to see what the heck I'm talking about, where no d orbitals are invoked. And so let's go back. So again, formally, right, our hybridization is sp3d2. So we have 1, 2, 3, 4, 5, 6, right? So kind of giving us 6 lobes here. And I'll write it in our cheat sheet. So sp3d2 is equal to this 6 lobe monstrosity that I obviously can't draw. And so before we just kind of, keep plugging along, I do want to point out, look at what these all look like. And this is literally what it is made out of and why we did not need to invoke d orbitals. And now I'll put it over here. And I'll rewrite it for a second. So sp3d2. And so if we take, right, our pz, so our pz obviously looks like that. And then, right, our py, so it's going to go in and out of the plane of the board, or we could put it as at a slight offset so we can actually see. So py, px, and again, I'm a horrible artist. But now we are seeing, okay, well, I have 1, 2, 3, 4, 5, 6 lobes there. So yes, we can use entirely p orbitals to get us to this 6-lobe monstrosity. And then there are s's probably mixed in there as well, but again, this gets into kind of deeper level stuff. But the point is to say that we only needed p orbitals. We only had to invoke s and p orbitals in this. So no d's were harmed in the making of this. All right, so let's think.
Is there an additive formula for that? The same way there was for the others? It's like,
It doesn't work out as nicely, unfortunately.
So you're saying like falls apart after 5?
Yeah, yeah. So because what it is it is just the p orbitals, and the s orbitals like mixed in a certain way. But to fully understand it, we'd have to get into symmetry and point groups, which is a topic for an inorganic chemistry class. And we'll kind of like dance around point groups. Point groups will come up again in lab, but we're not going to be tested over them. We're not going to learn them, know them. We're just kind of going to appreciate that they exist and they're a thing. But. All right, let's see if we still have time. So we want to start with our fully symmetric AX6, or we'll do sulfur hexafluoride as our classic example. So SF6, and of course I should have stated the geometry, so octahedral geometry, very important in organometallic chemistry as well. So yeah, you'll be seeing probably a lot of octahedral geometry throughout this course. And then we'll just practice drawing octahedral. So, right, we have 2 fluorines and what I would call our PZ axis here. And then trying to draw them all nicely spaced out in a square planar fashion. It's kind of arranged about. So, of course, again, I'm using my dashes showing that those fluorines are coming out of the plane. And these are, of course, going behind to give us, again, our octahedral geometry. And then octahedral, I will say, this is one of those where you often see it kind of tipped in a different manner. Let me see if I can draw this. Again, I'm like a horrible artist, so. So this would be the other way to draw octahedral, where it's kind of like tipped on its side. So you can kind of see, right, if you took these 3 fluorines and put them face down, it would look something like this if I wasn't such a bad artist.
Would it be acceptable to put physical wedges on the fluorines so that everything is sort of, opposite?
I think it has to be in this orientation. You mean like flip the wedge back there?
Yeah, make the.
Then that would look like, yeah, I don't think that would make kind of sense, but I'll try not to be like too picky either with these structures. You know, again, I'm not much of an artist, so I just want an attempt. All right. Oh, last few thoughts. We should at least, again, write down the electron and molecular geometry for this one. So obviously the same of octahedral, and then we'll continue on Thursday with the rest of this. Oh, and then, so yeah, obviously Thursday we'll just lecture, and then for y'all who haven't had me before, usually we do our quizzes on Thursday in the second half during the recitation period, but Yeah, tomorrow we'll probably just lecture, or maybe we'll play around with WebMO some more or something. Or not tomorrow, but Thursday. All right, I will see y'all in lab shortly after the migration. And please feel free to take more magazines home. They're for your pleasure. And then,
I gotta go. I have to go to the website.
any last minute questions online?
Unfortunately, gone the week of finals. So, but I'm not gonna be gone on Thursday, so I'll still be able to take the lab final if it's gonna be the same thing.
Yeah, so I'll do the final the week before, like I did. And then if you wanted to take like the final on that Friday or something beforehand, or?
So I'm gonna be back on that on the Friday of finals. So are you still gonna be in the lab on Fridays?
So I don't have a Friday lab anymore, but we could still do like a makeup time during that time if you need it. Or
Okay.
the testing center should maybe have more availability this quarter.
What I'm kind of worried about because I already talked to my calculus teacher about it because I have the same problem like same day too actually because